Hello, everybody. Welcome to another day of PowerShelling and summiting. First of all, the session is AIML with H2o and Windows PowerShell. Hopefully you're in the right room. As far as who I am, why am I up on the stage? Why am I talking about this? Number one, I work in New York City. I work for a Fortune 100 downtown. Over there, I spend time working on distributed computing and sort of cloud computing platforms and those types of systems. That's kind of where I spend most of my time. I do not work as a data scientist, nor do I work as a machine learning expert. I simply am a hobbyist, so I've taken some Coursera courses from the Stanford Coursera course. I've implemented a bunch of these algorithms kind of by hand from scratch, just for academic reasons. And what I found is that this stuff is actually accessible now, right? So what we're going to be talking about today is stuff that you can embed into your applications, build data models, work out predictions, clustering type algorithms to help in whatever way you think that it might fit the applications that you're developing. Within my company, I enjoy looking at the infrastructure side of this. So I like spending time with data scientists to understand their problems so that we can understand how to build the cloud computing systems underneath it to be able to figure out how to distribute these problems more easily, how to help them get their processing to happen faster, et cetera, et cetera. But again, that's not my day job. The third thing is that I do spend a lot of time with some PowerShell. Some of you may know me through the years. So I think 8 times MVP award recipient. I founded the New York City PowerShell user group. I also founded, there's a Techstravaganza talk that we do in New York City every now and then, which has an entire PowerShell track to it. And I spend a huge amount of time working with bringing things that are happening outside of the Microsoft ecosystem and the PowerShell community and bring them into it. So helping people see that there's these frameworks that exist out there that people are leveraging all the time. So today we're going to be talking about H2o. Tomorrow I'm doing a talk on Apache Zookeeper and writing clustered applications with that. Okay, so that's why I'm standing here right now. So if you're going to drill me on a lot of the data science questions, I probably will flounder a bit, but I'm going to do the best I can to at least give you some starting points. And it's sort of a soup to nuts. So you don't have to have any experience with machine learning. You don't have to have any experience with H2o. PowerShell will definitely help because we're going to be looking at basically invoking a lot of REST methods through this and understanding the web commandlets, which I think there's an hour and 45-minute talk happening right now on exactly how to use them. That's actually the stuff that I'm leveraging in this to be able to access this platform. So what is the platform? Why are we even talking about this? What is H2o? Most importantly, it's an open source platform. Okay, so H2o is a company. There is an enterprise version. They build on top of the open source and add all this color and make things super easy for data scientists in the future. That's where they're headed. I'm not talking about that. I'm talking about what's open source, what you can leverage today, what you can embed in your applications in your PowerShell code. The next thing that I really like about it is that it's API driven. Okay, so there's a couple of SDKs out there. There's Python and R that come out of the box, and all the books that you're going to read have those 2 languages in them. There is no PowerShell one. So what I would recommend is that all the prototype code that I'm going to be showing today actually could be converted into a module very, very easily. And it's something, if anybody's willing to take that on as a project, I'm happy to handle that code, and it's all MIT licensed, so you can feel free to play with it and do something with it if you want to get into that. Fantastic project for academic reasons if you even just want to understand how to build a module and out of something that's REST driven. Okay. The next thing is that because it's API driven, that makes it cross-platform. And what that means is it's not just cross-platform, but it's actually you could have multiple languages using the H2o framework at the same time. So I can have Java application set up a data model, and then I could have the PowerShell connect to that instance and leverage that data model. Or I could do it vice versa. It's completely interdependent. H2o is a Java application on its own that spins up. It's a server, so it will maintain the state while it's living, and when it goes away, we lose the state of everything that was there unless you serialized some of that stuff out. But the point is that it's cross-platform, so it will work from multiple languages. The next thing that's kind of interesting is that there's a GUI for doing all of this. And what I'm going to be showing you today is a series of demos, and we're going to start in the GUI because the way the REST API works is it's translatable one-to-one based off of the GUI. So if in the GUI I train a data model using these parameters, when I go to PowerShell later, I will use those same parameters and I will go through the entire workflow the same way. The GUI is actually pretty nice for just getting and prototyping things pretty quickly, so you can learn how to do something and then turn that into a script that you can then repeat over and over. Another thing that's kind of nice about it is that it's self-contained, meaning that it's not dependent on a cloud vendor. So one thing, the API-driven idea is not new. There's plenty of people doing this, right? Azure ML is starting to get into that space. AWS SageMaker kind of works this way to a degree. And there's this proliferation of libraries that are sort of coming out here. But the point is that the API-driven thing isn't new, but what it means is that I don't need to have a cloud vendor for it. I can run this on-prem. I can run it in a cloud. I can do whatever I want with this open source bit. The next thing that's super interesting is sparkling water. Gotta love that library name. So that sparkling water is a combination of H2o and Spark. So if you don't know Spark, Spark is a distributed computing platform that provides you, so you can have clusters of these Spark instances. And what sparkling water actually does is any algorithm that you would pick and you start to train a data model on, if it could be done in a distributed fashion, it will leverage your Spark clusters to do so. So if you happen to have Spark clusters, this is fantastic. Or if you can spin up Spark clusters on demand for this type of processing, it's really neat. I toyed with actually doing all my demos with sparkling water, but I only really have my laptop, so we're going to do a single instance H2o for all of this stuff. But it's pretty simple to spin it up. Okay, the next thing that I really like about this is that there is a flow, because the company H2o is in the business of making this super easy to productionize, the data models that are built on it. They had another open source project called Steam, which is now deprecated, but it still exists. And you can basically fork it, you can compile, and there's one particular bit of service that's open source there that will convert the data models in H2o into REST services. And it's really cool. So this is a way to basically export out of H2o, get a WAR file that you could then run as a web service somewhere that you could then invoke via PowerShell, right? So you don't necessarily even need H2o after you've trained up your data. And I don't know if this is the final one, but grid search and AutoML. The other thing that's really nice about this platform is that it provides you, so when you start working with these algorithms, and you're going to see in a second when I show you like the first algorithm and we look at all the parameter options that are there, it's blinding. Like there are so many parameters and they all do things and we don't know what half of them actually do, right? Data scientists may. Some of them, when you talk to them, they're like, oh no, I like to play with these parameters or I like to try these things. But there's no hard and fast rules of like this will always work and this will always work. So the answer to that is what's called grid searching, or there's another technique called Bayesian optimization, which is actually even better than that, which H2o doesn't have out of the box, but there is a third-party library for that. But the idea is that I can test a whole bunch of different parameters against my data, my algorithms, try a whole bunch of them, and see which ones turned out the best, and evaluate which model I want to use now. And so that functionality actually makes this really easy. And the AutoML one is the super easiest of them all. It just takes a little while to run. That's a no-brainer. AutoML, here's my test data. Find me the best thing possible. And then a couple hours later, it'll come back with a bunch of data models that you can look at and evaluate. At which point, you could then say, all right, this algorithm seemed to work best for this data set. It seems to be pretty consistent. You know what? In the future, I'm not going to run all of them. I'll just do grid searches on just that one algorithm now. Okay, so it sort of simplifies things for you, and it's very easy. So this demo, this entire thing that I'm doing right here, like we're going to train up some data models. We're going to look at some of the open data sets that exist. Almost all of it could be done in like 5 minutes of all the demos that I'm doing today. But I'm going to take a lot of time. We're going to go through each of the arguments. We're going to talk about what is actually happening under the covers and kind of get a little bit deeper with it. Okay, so as far as what we're going to be covering. So we're going to start with H2o. I'll show you how we download it, spin it up, how we access it. We'll talk about the user interface, so H2o via Flow, and we'll train up our first data model in that. At that point, we'll also look at REST hacking. So I'll show you how you translate from the web UI into PowerShell. We'll then we'll generate some data models. We'll create it for, like I said, a pair of open data sets. Iris data, which is predicting the flower type based off of the dimensions of the flower, as well as the MNIST data, which is handwriting recognition for digits, numbers. And so we'll look at both of those. We'll also look at not really mathematics. I'm not going to go into the mathematics of this, but what I have found is that at least understanding from a visual perspective some idea of what the math is actually doing is very helpful in understanding what you're actually doing. So again, there's going to be no numbers, there's going to be no symbols during the mathematics part, but you will see some charts and graphs, and I'll explain what's actually happening as we go through this. I'll also do a demo on unstructured learning. So this is the idea of finding clusters and groups of common patterns within your data sets. So the greatest example of this is like the Netflix recommendation engines, where how do I bucket, let's say I want to bucket the world into, let's say I think there's 50 different types of people in this world. I want to find out which movies they've been liking together or figuring out, and so we find like little groups that we think that they'll like, and then we can maybe recommend those additional movies to them. We'll do a demo on the grid search, so the parameter tuning. I'll show you a demo of productionizing these data models and turning them into REST services that you can access from PowerShell much more easily. And then we'll do a demo of AutoML and look at the additional resource. Big day, big day. Everybody get ready. Hands up. Now, that's the end of the slides, though. I promise the rest of it is pretty much all in code until we get to some of the math stuff. All right, so the first thing that we're going to do is we're going to start H2o. So H2o, you download from their website, so h2o.ai. There's a latest stable release which you can get, and the instructions to install are pretty simple. Unzip, run java-jar to the jar file that they have. Okay, that's kind of hard to see, but 3 easy steps. And what it looks like over here is simply, so I have a folder already where I've downloaded a whole bunch of files, so let me just show you what's in here, so this way you can see. I don't know how well that's visible, but in this directory, I'm going to highlight the things that didn't come with H2o. So really, it's just anything that's unhighlighted is all that came with it. The H2o jar file is 86 megs, so it's not even that bad. And then what happens is it looks like this. So java-jar, and we will run this H2o. Obviously, you have to have Java installed. Don't ask me about versions of Java or anything like that. I really know nothing about Java, so I just know how to execute and compile. Okay, this actually usually takes only a second, so hopefully I'm not getting the jcool curse, but looks like we're all right. Okay, so it spins up H2o, and then it gives you this H2o flow browser. Don't ask me about securing this at the moment. There are plenty of documents that you could find online about all of that stuff. I'm just simply going to be pretending that there is massive security and that I'm the only one who can access this. Okay, this is what the interface looks like, and let me make this a little bit bigger so you can see stuff. Okay, the interface, if you have played with like Jupyter Notebook or Zeppelin notebooks or any of the notebooks that exist, web notebooks, it's kind of a similar in its idea. These are actually what's called cells. So in each of these cells, I can clear this. And what actually is happening is if I can rerun any command that I've run, so I can come back up to here, I can hit Shift-Enter, and it'll run that again. I can also run that assist command just by hitting this button, and it'll keep, every time I do something, it's basically going to just add something to the bottom. It's called a flow because you're showing kind of the flow of how you're doing this data manipulation, the modeling and processing, and all of that stuff. Before we also get into anything real, I also want to show on the right-hand side the help actually has a decent amount of stuff, which looks like it's a little scrubbed here. There's examples, and I'll be showing one. We'll actually be going through the k-means clustering later in this through one of the examples. And then there's also the H2o REST API documentation, which is actually embedded in here, which is super helpful when you're using this with PowerShell. Okay. So this is the interface. So the first thing that we want to do is we actually want to import some data into here. Actually, I'm going to take this really hot in here. So the first thing we want to do is we want to import some data. So let's actually talk about the data that we're looking at here. It's called the iris data. It's actually a very small data set, which is really interesting when you think about it, because we're talking about 150 rows, I think it is, 120, 150. Whoa, too far. Yeah, so 150 rows. So it's not a huge data set. And all that's in this data set, so you've got, this is a CSV file, so you've got the sepal length and sepal width, which is a dimension of the flower. You have the petals length and the petals width, and then a definition of what that actually is. So in this case, you can see that this is an iris setosa, and if you come down here, you'll see that there's 3 categories of flowers. There's iris setosa, iris versicolor, and there is iris virginica. And what we're going to be doing today is we're going to be saying, we're basically going to be trying to train using this data set to say, okay, with these inputs, these 4 columns here, we know that this is going to be this class. So build me a model where if I give you those dimensions in the future, you can predict what class of flower that actually is and tell me with what confidence you think it is. So that's what we're actually doing. So let me pull this data into H2o. So the way we do this is we import files. So I will take 1 second just to show that, so the sort of web hacking here. Control-Shift-I on Chrome, use your inspect. The network bit right here is actually the one that you want to watch when you're looking at this stuff. But here I will, so you can see it's doing a whole bunch of lookups right now, which I really actually don't really care about. What I care about is the next thing that happens. So after I add this, so let me clear, and I import, you can see over here on the right, I can see the path. So the URL that was used, I can come in and I can look at the actual post data that was sent to it, as well as look at the response data pretty easily. And what you'll find is that when working with H2o specifically, there are some things that the JavaScript, the web GUI does and implies, and so you're not sure that you don't realize that it's actually like a 2-step process. Instead, it looks like a 1-step process. And so probably the biggest example of this is the next one, which is parse this file. So we've imported it, and now we have to parse it because it's a CSV file. When I hit parse over here, it does this setup parse function, which actually is the function that was called here. Okay, the parse setup is actually kind of interesting in that it makes some predictions about what types of data you have here. So it finds that these are numeric. It's giving me an enum for the class because there's only 3 of them, so it's a better way than string. So it's done all of this for me. But the problem is that once I have this, what I actually am doing when I click parse is I'm taking all of the outputs that were here in that above thing. So anything that was returned from that parse setup, I actually have to pass into the parse files function, right? And so I'll show you the helper code in PowerShell when we get to that in a second. That'll make this a little bit more easy and make you understand what I'm talking about here. But for now, just know that there is a lot of things that you may have to take from one function, get the return value, manipulate in PowerShell, and then send it off to the REST interface for the next one. Okay, so we now have this iris header data in here. And when we have data in H2o, and actually let me close this so it's not so cluttered. So when you have data in H2o, the first thing that happens is you get some statistics on it. So we can see a little bit about the data. I can see that, okay, look, the min here is 4.379 max, and the averages, et cetera. I can also see in the enum that there's 50 that are labeled 0, which is actually expected. So generally, like missing or 0 you may be concerned about. It's more about data quality and just making sure you have a good data set. However, in this particular case, an enum is 0, 1, 2 because it's ordinal. So therefore, there are 50 of one class. So that's why that shows up as 50 zeros. This does raise a very, very good point, though. PowerShell is one of the best languages ever for data manipulation. So, because of the fact that you have your filtering, you have your conditionals, your where clauses, all of those things that are built into the pipeline, data manipulation actually is better to do in PowerShell than in something like H2o. I'll also say, having done this in pandas on Python and using some of those data frame type technologies, that PowerShell just blows it out of the park as far as usability and making things simple to do data manipulation. So what I would suggest is you wind up doing anything that you have to fix the data, you do in PowerShell, send that out to CSVs and then import it into H2o. It just makes your life easier, so this way there's less of having to figure out like what settings and what data types and things like that to use. Okay, so I have data in here. The next thing I want to do before I do anything is I'm going to split this data into 2 sets. I'm going to basically say I want 90% of this to be one set, and we're going to call that our train data. And then 10% of it is going to be my test data. And this is a pretty common pattern to split up data sets like this, do it randomly when you're training your data models. This way, you can use the data from your train, that 90%. I can build my model from that, and then I can validate the model against the test data to see exactly how well it did. We're going to talk a lot later about overfitting, which is this idea that you've made it so that every bit of test data works, or train data works perfectly. But nothing on test data ever works because it's so like hyper-fit to just the one particular set of data. That's something that you absolutely have to avoid. Anyway, in this point right here, I've got my train data and I have my test data. The next thing I would do in H2o, so I'm going to call my assist again so I can get my things back, is I'm actually going to build a data model out of this train data. Actually, I could do it from here too. Oh, I'm sorry. The one other thing I wanted to show you guys was that there's also the ability to view the data. So if you wanted to actually see what was in there without having to load into Excel, see what it looked like, you can get a sampling from the system. Once I have that, so I have my trained data right here, I can now build a model. Okay, this is where the fun happens. You have to choose an algorithm. What do we choose? Anyone want to pick one? Bayes. Yeah, I mean, the honest truth is it's very confusing to figure out what, especially when you have no understanding of what any of these are doing. What I can say is that there is a algorithms page on H2o right here that has a list of, it's got a list of like the common sort of parameters that are used by all of these things. And then they have them bucketed into 3. So there's supervised, unsupervised, and miscellaneous, which is really NLP. That's natural language processing, which is basically taking documents and tokenizing them in a way where they could then be used by machine learning. I'm not going to be talking about that today. We're only going to be looking at the supervised and unsupervised. Supervised basically means that there is a category in the data set. There's something that we know what it actually is. So in the iris data, we knew that each flower, what class of flower it was. In unsupervised is, again, it's like that Netflix recommendation in that you want to find groupings, but you don't know you don't really know what it's going to be. And so what you want to do is make an algorithm in a way where, or make a model in a way where if I send it some data set, it would tell me which group it would belong to. That's kind of the goal with those. So those are the 2. Now, as far as choosing one, well, they're all kind of crazy and different. There's a lot of parameters. So this is the documentation just for one algorithm. And if you look here, there's a lot of stuff that can go in here. I don't know what half of this stuff does, to be honest. And I'll be completely frank. It is a matter of tweaking, figuring. You can read up on these things. As you're playing with it, try a different parameter another time. Expand your understanding of each of them as you go, as you look for better data models. But for the purpose of our experiment here today, I'm going to show you the simplest way of doing these. And I'm going to actually just choose this gradient boosted machine. Although, to be honest, they're all the same. The interesting thing is that what we're going to show is that the interfaces that I'm doing right now, the very basics. So a training frame, I know it's going to be this train data. The validation frame is the test data I created. Enfolds is probably the most interesting one to think about in that there's techniques of cross-validation so that it's kind of like without having to have the train and test data separately, it does some interesting randomizations to try to prevent overfitting on its own, but I'm actually going to just leave that alone for now. And finally, I have to tell it which column is the column that is the thing that we're predicting, right? I don't have to ignore that column because it knows that that's the one I'm predicting, so it's not going to include it in the inputs. But so at a very basic level, that's all the information I need to submit to it. Like I said, there's a whole bunch of other things, and we'll talk about grid searching and how you can tweak these later, but let me just show you how we build a model very quickly. So that's done. Oh, no, now it's done. That data model now exists. So I can look at that data model, and I can see some statistics on that data model. So first I can actually see how it was built, all the parameters that were used. I can see log loss in this case is what's used here. Another one that you'll see me pull up is this thing called MSE, which is like the mean square error, which is in all of these cases, it's a matter of trying to get the number as close to 0 as possible, because that basically means that it's fitting really nicely. Here you can see that what it's using in its data model. This is actually really interesting. Petal length, petal width, it feels that it needs to know that information to make the prediction. The sepal length and sepal width is actually not as important to the classification of this flower, which is, it's just a fascinating fact, right? That you may not have gleaned from this data by looking at it, but now as you look at the way these models are interpreting it, you see how it's used. Underneath there, you can see how it was performing. Actually, this one is performing pretty poorly, to be honest. Even in the training data, it's getting about 4 wrong here, 3 wrong there. The validation data, it's actually done pretty well, where it's only getting 2 wrong out of the full set. But anyway, the point is, like I said, eventually we're going to be tweaking this and trying to get these better and better. But for now, we have a data model, and we can do predictions. Like, the work is done. Now the question is, how do we use it? And using it is actually just as simple as importing some new data that we want to validate and then predicting off of that. So let me do that right now. I have a file that I created in PowerShell, which I'll show you the code in a little bit. It's just 1 row. It has this input, so 5.1, 3.5, 1.4, and 0.15, and it's going to tell me what flower that is. So The way I do that is I can basically say first import that data. So we're going to go through all the rigmarole that we did before, which is fantastic when you have PowerShell because you can just do it quickly. So what was it called? Predict. Okay, so we import the data, parse the files. We're going to parse it, set up the files, parse the files, and then the job runs. Also, another thing to note is these jobs, anytime the job screen comes up, that's an asynchronous call. And I'll show you in code in a little bit how I turn asynchronous calls into synchronous calls, because there's basically a callback lookup URL where you can see the status of the jobs. There's a whole job subsystem built into H2o for this purpose. Okay, so I've imported the data, and now I'm going to go back to my data model. So I get my model, and I am going to predict using this model. I'm going to say, okay, use that predict data, the set that I came in, and predict. And so now I can look at that result, and I can see that there is 1 row, 4 columns, which was expected. And what comes back is it's saying that it's an iris setosa. And then I've got 3 numbers here. This took me a long time to figure out what the heck was going on here, especially in code, because this got really confusing. But this is percentage of confidence. So in this case, it's saying with 100% confidence based off of this data model, this is iris setosa. It is impossible for it to be versicolor or virginica. And you'll see in other data models when you run it, it actually has different percentages and of what it thinks that its confidence is. Okay, that's it. We did the bulk of the hard work, right? Like now you could actually leverage this thing and use it. So what's next? The next thing is how do we do this in PowerShell? Hold on, let me just make sure. Okay, how do we do this in PowerShell? So for this, I'm going to basically do the same exact thing. We're going to use a different algorithm. This time I'm going to do a neural net, because neural net's the hotness, right? That's like the real machine learning, which I'll explain why it's that way in a bit. But I want to start from scratch, so I'm going to actually restart my H2o. And when I do that, like I said, it doesn't serialize the state down. So in a second, this will come back, and we'll see that it's blank. So we're starting with something from scratch. Oh, there it goes. Okay, so if I do get frames now, I should see nothing. And if I do get model, I should see nothing. So this is a blank H2o with nothing in it right now. The next thing I'm going to do is let's build up my PowerShell environment. What the heck is that? Windows Inc. I don't even know what that is. All right, layered here, and I'm going to create, so apologies, I know you guys aren't used to VI, but I am. So I'm going to, up at the top, put the code and the scripts that I'm going to be looking at, so my doit.ps1. And then down at the bottom is where I'll be pasting and executing and that kind of stuff. Okay, so there's 2 functions I have to talk about before we get into actually using the REST API. The first function is this convert to form data. This is the bit that I was describing before. I'm going to take the return value from that, let's say that parse setup function, and pass it to the parse function. All this function is doing is it's taking an object and it's looking at its properties, and it's basically saying, okay, if it's Boolean, well then the property chain that's going to be posted into the form data says basically give me that property equals true, and then I'm adding the ampersand. And then I go through and I do the same thing for arrays. So collections are basically formatted in with the proper syntax. And then finally, anything else is just key value pairs, right? So we just output plus equals property and the ampersand at the end. And then at the very end of this function, I remove the last ampersand, right? So this way, I now have a complete post sort of URL of that data that I can throw into the function that I'm going to call to the REST API. Is that clear? We got sound good. All right. The next one is how I turn the asynchronous calls into synchronous calls, or at least give you a hook to be able to figure out how to pull it and look at it. So the way I do it here is I use a wait H2o job, which takes a path. So what I'll show you in a bit when we look at the return values is that it provides you a URL, and that URL, or it's not really a URL, it's the path part of the API URL. And then we'll add that to the REST API, so this way you have the callback. And then I query that. Right here, it's every half second. Actually, I'm going to change that to 2 seconds. I think it makes my machine crash less when we do some of the really deeper neural net stuff in a bit. Okay, the next thing I have is the URL. So this is the base of the API. I'm just constantly using localhost. I could have parameterized this. There's so much I could have done. This is prototype code, please. This is not production grade code. This is just proving the idea. Okay, if you're not familiar with this syntax, hopefully everybody is, because this is pretty much the way I do all of my string manipulation, is to use the old VBasic templating within your strings. So if you're not familiar with this bracket 0, basically when you do -f in a variable there, anywhere that first variable is going to go into all the $zeros, and then these are all going to go into the into the bracket zeros, and these are going to go into the bracket ones. And that's just a way to quickly sort of template and then add content to the strings without ensuring that there's fidelity. The next thing is I have my iris URL. So this iris data, I did manipulate. Oh, good call, good call. You could have let me burn for a while. That could have been fun. All right, so iris URL. So the original demo, so I have the code sample that I'm showing right now is on my blog. So powertoe.wordpress.com is the last blog post. It used this from the internet, so it grabs it in real time and pulls it down. But just because I was worried about demo gods and all of that, I downloaded it locally, which actually required some of the later calls to be changed a bit. This parse setup body actually had to be changed a little bit, but it's like a syntax thing. Basically, H2o, it all has to do with like the destination frames that it interprets and the names. So I'll spare you the details on that. It's a little bit of nonsense. Anyway, we should be abstracting those into better functions, which I do a little bit later. Okay, the next thing I have here is the first function that was called, right? So in the flow that we did earlier, we did the import files function. And so here you can see me calling that import files function. All I'm doing is changing the body. I'm setting the path equal to the iris URL, which is this local one. And then I'm invoking the REST method, and I get a return value. Okay, that return value is, kind of holds most of the data and stuff. And actually, I'm going to run this right now. Actually, I'll run it up to here. So then the second command after this is parse setup. So parse setup is that one that ran, and I needed that return data back. So that's why I kind of want to pause there so you can see the output. So let me just comment the rest of this out, and we'll run this. So chuckling at my environment.
I was looking at your decision to comment it out as opposed to like
Yeah, no, this is just easier. This is Vim style. All right, anyway, so I have this stuff here, and what I really want to show is this return value. If you look in here, there's all that data that actually gets pulled back. And then if you look, what I'm going to do in a second is I'm going to take that output from the other one, and actually I'll show it this way. Okay, so I'm going to take the output, and I'm selecting these parameters from it. I'm then going to pipe that into that convert to format to form data, which is then going to convert that into the post that I'm now going to submit back to the REST API. Everyone follow? All right. This is the actual PowerShell stuff. You guys should know this. All right. So let me comment back this out. And here I'm going to actually invoke it. And you can also see, and I'll do it up to here. So what I'm next going to do is I'm going to call the parse function. And I'm going to invoke the REST method. I'm going to get the return value. And what I want to show you before I run it is this return job key URL. This is the path that I was mentioning gets returned back in the asynchronous calls. So if I look at that, it's just a path here. And that's the job subsystem. So this is the job that's running in the background. And then now if I run my wait H2o on that, it is actually already done. I mean, this took a couple seconds, but just for the sake of completeness, it says it's done. And you can see that it basically has been applying the same pattern, and then it just adds that to the REST API call. Okay. Next thing we're going to do is call the REST API for splitting the frames. So again, the rest of this is all pretty straightforward. I'm really just doing everything that was done in Flow, and the way that I found out what parameters to supply here was by doing the inspecting the network messages and seeing what's actually getting passed when I was trying to do something that I wanted to do, looked at what it was supposed to look like, and then applied it within the code here. If anybody wants to do the open source stuff on this, it's really a matter of understanding, taking each of these API calls and turning them into functions, to be honest. It's pretty straightforward. Okay, so we're going to split the data, and then finally we're going to train the data using this time we're going to use a deep learning model. So you can see this. So that's the more black box type stuff. And we'll pull that data back, and then finally we're going to predict. So the next thing, so this prediction is the exact same thing we did before. The difference here, it's actually, we were going to predict off of the, apologies, let's just do it from here. So this is going to predict basically off of the train data to tell me, the test data to tell me how well that model is performing. So I'm actually going to just run this whole thing again. Probably get a couple of errors because I've already imported some of this data. Oh, actually, you know what, for completeness, let's just restart it. Okay, so it's up. And then this time, I'm going to run it basically up to this point so that we can train the data model. That's not it. Okay, loading the data, parsing the data, and it is splitting the data. It is training the deep model, and it's done. Okay, and then if I look, it's validated. So that just did a neural net for me in, what was that, a couple seconds? The neural nets actually do take longer with larger data sets, and the MNIST data that we're going to look at in a little bit, which is like 20 megs or something, is going to take 10 minutes. But it's actually not that bad. And here you can see that the MSE, so it's about 3.12. This is actually a really bad data model. This one I would never, you'd need to tweak it because it's not that accurate. I only know that because I've done this data set so many times and seen the results of what good data models look like, so I can tell you that that's actually not that good. Finally, the last thing that we're going to do is do that prediction. So you can imagine now, this is one way that you can load these data models into H2o. We can also serialize these and reload them in, but the idea is that they're living in H2o now. So if this data model exists there and I want to ask it for a prediction, it's as simple as this code. It's all I'm doing is I'm creating my CSV file, right, for the thing that I want to test. I create it as an ASCII file right here, so predict.csv. I then call all the same functions before, the import, parse, setup, and parse. Finally, I do the prediction. And I use that same data model, and I predict off of it. And then at the end, we get a result back. So with all of that said, let's actually run the whole thing now. And we should see, so I will wipe it out completely. Okay, so we've wiped, it is up, and we will run do it. So we should get, let's see if the MSE gets a little bit better. Splitting the data, training the deep learning model. Ooh, oh, that's because the file already exists and it was open, sorry. The data I was serializing down to predict. And here you can see that it predicted with 99% that it is Iris setosa. And remember I said that it took me a while to figure out these numbers, the probabilities. It was especially I just kept looking at the E-05 and not realizing how small of a number that was. But anyway, that's there. And that actually, what I'll show you a little bit later is when we export these data models, this is how it always returns the values to you. It shows you with what probability it thinks it is one of those things. Okay, it's pretty cool stuff, right? Yeah, feeling good? All right. The next thing I want to do is I actually want to look at a more complex data set. And then I'm basically going to run the exact same thing, but we're going to do it with the MNIST data. And I love actually showing what this looks like. So the first thing that we do with any of these projects is actually look at the data. So here I have MNIST, and then I actually have some code in here called import and render. So import and render is basically, and let me just start it. So import and render up here, the function that's running right now, is basically going to import the CSV file. It creates headers, because there's no headers in this data set. So let me explain what's in the data set first. It's columns. The first column says a number. So it's a number from 0 to 9. Okay, that's the number that the pixels are. The next column, the next set of columns are individual pixels. So it goes from like upper left all the way across, and then it kind of repeats, and it tells you the shading value of each one. And so what I did was I wrote a very quick parser that will visualize what that looks like. So here I've taken the whole data set, I'm getting one sample out of it. So the sample looks like this. Actually, no, the sample does not look like that. The sample looks like that. No. Oh, I didn't dot source it. We got to do it again. Okay, dot source, let's let that run. Anyway, the point is, so here you can see that I basically am getting one sample just to see what the first value looks like. I'm splitting it so that I can look at the value as well as that pixel array. So I've got those two variables right now, value and pixel array. Value is, again, the value, which I think is the number 7, and then the pixel array is going to be that list. And so here you can see it rendering what it looks like to render the number 7 in ASCII. What it actually looks like in the real world, there's way better visualization out there for this, but these are what they kind of look like. They're hand-drawn numbers, okay? And the goal here is that when you look at this data, right, this is not something that we can interpret. Well, maybe some people can, but so for example, here's the pixel array that's the number 7, right? Obviously, right? So it's just gradient shading on each of the pixels, and then we know that equals the number 7. And so instead what we're going to do is we're going to train the same way that we did in the iris data, but it's a much larger set of columns with not that much commonality. Like, we don't really understand this data set that much. And so we're going to apply a neural net to it, because the neural net's going to kind of figure out that for us. It's going to do some black box and kind of put it all together for us. And the goal with this is, again, to build a data model where if I supply a new pixel array, so a new image, it will tell me what number it thinks that is, right? That's the goal with what we're doing here. So for this, I'm going to run this. Like I said, it takes about 10 minutes to run, so I wanted to, and actually, let me just make sure we clear. I just want to clean up H2o so it doesn't have cluttered stuff. Oh, actually, meant to show you. The data model we just had is actually in flow right now, but I just killed it, so I can't show it to you. But I'll do it on the next time when we do the deep learning one. OK. There it goes. So now we'll run the MNIST. Oh, and let me show you what that code does. So this is the form. This is the code that we're going to run. It has the two functions, the convert to form data and the wait H2O job. There's also one additional function I wrote in this one, which is import H2O data. So those 3 steps, which were really tedious to look at, and 10 lines of code each time, I created into a little bit more of a function. So you can say import H2O data, give the path to where it exists, give it a name that you want to call it in the data frame. I've been using that word data frame. I don't know if I explained it, but data frame is really just a data set. Everyone gets that? OK. So we give it a name, we pass it the API URL, and if we want, we can supply a list of columns if we know it doesn't have a header in it. It then runs those 3 sets for us, so this way we don't have to look at all this code anymore. Now it's simplified down to this. So we run the headers, and we import the 2 data sets. So the way this MNIST data works is they give you 2 data sets. They give you a train data and a test data. These are open data sets. You can download these. There's open source licenses for most of them. Kaggle is actually an interesting place to look for some of these data sets and challenges and things that exist out there. But you can download this stuff and play with it yourself. And so here I'm going to import this data. I'm going to call one test, one train, and then I do the whole thing again just with the neural net. And that's all that's going to do. So let's run that. And then we're going to take a little bit of a... All right, so that's going to take a few minutes. Everybody stand up, stretch. I'm not kidding. Let's get up. Another thing is this is Mrs. Whiskers. Mrs. Whiskers was sent by my daughter. She insisted that I had to take Mrs. Whiskers with me. So what I'd like to do is actually get a little picture with all of you guys and Mrs. Whiskers. Everybody could raise your hands up. I think that would look nice. Yes, Mrs. Whiskers. Actually, wait, even better. How about everybody on the count of 3 say, Mrs. Whiskers says hello from Washington. 1, 2, 3. Mrs. Whiskers says hello from Washington. All right, thank you guys. Appreciate that. All right, now that the blood's moving a little bit, let's talk about some mathematics. Woo! All right. As I promised, I'm not really going to be doing too much on the math side, but let's pull that up. OK. Public domain image. I love these things. I can actually put them in the presentation. Okay, so this is the problem. Right now, I'm training a neural net against a massive data set on my laptop. So looking at these images might be a little slow as we go through this. Okay, so the first one I'm going to show you here is, and you know, I should mention also that we've been calling this talk artificial intelligence, machine learning. Technically, some of that only applies to like the deep learning type stuff. A lot of this stuff is just analytics. This is just mathematics that we've been doing for a long time. What I like about these visualizations, though, is they kind of explain what we're actually trying to do. So in this example here, imagine that the stuff on the left, that column on the left, is actually our value. That's the thing we're trying to predict. The thing on the bottom is the input, right? So there's a number, and we know that what we want to say is, okay, at 0.5, where do we think that dot will be for the 0.5? And so what you wind up doing is you build these functions. So in this case, this is a linear function. All it's doing is it's trying to find the easiest way through this. This gets really complicated, though, and it's actually fun to kind of go through the mathematics on these because you'll find stuff like, imagine if you had an outlier, right? So if there was a data point, let's say up here. Ooh, I think I just killed my zoom. OK, so let's say there's a data point up here. Imagine what that would do to the line. Like the whole line would shift up towards it, and then you'd have completely skewed results. So there's actually mathematics in figuring out where those are, those outliers, reducing that, you know, ensuring, and there's all sorts of things that apply to this. But at the end of the day, all that's happening is we're creating a function. We're saying, give me the input and tell me where it's going to sit on that line. Okay, that's what a data model actually is in this context. Another thing that can be done with this type of data model is, so this is a line, and we could say that on one side of the line, everybody has cancer, and on the other side, nobody has cancer. But it's genuine, right? Like that's actually how you know, these functions can be applied to categorization just as much. I want to talk about a couple of other things. So the line is actually really easy to understand. It gets a little more complicated if you add more variables, basically because how the heck do you put that on a two-dimensional chart, right? So that's not possible. So what I can show you is there's an article here. And actually, I already have them open, so I'm just going to pull it up. And that's going to take a second. And that's going to take a second. Fortunately, it's only 10 minutes for that thing to run, so any day now. OK, there we go. So this is a visualization of basically you know, what it would look like to map out multiple dimensions. So down at the bottom, you can see 2 dimensions, and then your value is at the top. So at the end of the day, again, these are just mathematical functions, right? These are, well, they're not always mathematical functions, but in this case, we're looking at them as mathematical functions. Okay, so you're finding lines that fit so that when you put the inputs into that function, where it gets graphed is the point at which it's the prediction. Okay, very easy to kind of understand it from that perspective. This came from it's a research paper from okstate.edu. I'm just trying to, all right, that's going to take too long there. Apologies, but I do have to give the credit. Any day now. OK, ordination okstate.edu. Sorry, that took so long. The next one that I'm going to talk about is overfitting. So now that we're drawing these lines, it's actually easy to see what we were talking about earlier with overfitting. So this is an example. All right, we'll call this the categorization one, right? The blue ones they have cancer. The red ones don't have cancer. Okay? There's a bunch of data that goes in and it applies. And what you're seeing here is 2 lines. You have a black line and a green line. The black line is a decent function, right? That actually gets the majority of them. And yes, there are outliers, right? So some blue dots in the middle of the red ones that don't seem to make sense. But you know what? It's fairly accurate to just incorrectly do them, predict on those. Now the problem is, of course, knowing the data set and how it's going to be used directly affects your confidence level. So if this really was cancer, we probably would not want, we'd be very, very sensitive about false positives and false negatives. However, if it's something like, you're looking for anomalies within your logging data, within PowerShell, like it's a much different story. You're OK looking at some false positives and false negatives. The overfitting idea is what if you actually, and some of these algorithms actually do this. They write functions that are so tight that they fit completely around the data set like this. So that, now the best example of this is in this bottom sort of portion right here. So imagine in that green bubble there, imagine the blue that's between the black line and in that green bucket, right? That would likely be a blue dot, right? Chances are, just by us looking at this, we can all probably agree that if it was directly even next to that red dot, it would probably be a blue dot. This model, when it runs against this data set, will be perfect, 100% perfect. But then when I start adding those variable things that are, would show up a different way, it's going to basically overfit it. So it's something to be mindful of as you look at these things. And that's why it's really important that you split your data into train and validation so that you can test it, and you constantly want to randomize those types of things and look at them more deeply and kind of evaluate whether or not you are overfitting, because it's a real problem. Okay. The next one I want to talk about is, so we've been talking a lot about the mathematical functions and the models. There's another type. There's what's called decision trees. So decision trees are actually pretty simple. So this is a GNU image from Wikipedia that I have to give credit to. When is this job going to finish? So Riz Karafik, which I actually have to. And GNU, sorry, just have to call the license. Sorry, this one is not GNU. This one is the Creative Commons Attribution Share Alike 4.0 International License. Okay. So with this image, I have an example of multiple decision trees. What is a decision tree? Very simply, I can think of it this way. Imagine that I started a question. I'm going to interview you. I'm going to decide what to do based off of these questions. First of all, how much money do you have? $0 to $500 in my pocket. We don't want to talk to you. I have $1,000 in my pocket. We want to talk to you. So that's a first decision, right? I'm making a decision there. Once we find out you have $1,000 in your pocket, we want to find out how many assets you have. Like, what do you own? What can I take from you also? And so we may find out, which buckets yes, no, I meet these thresholds. And so if you're a big whale, I want to go after you. I want to sell you some investments or something. So a decision tree is actually very simple to put together, and we do them all the time. They're just simple yes-no logic flows. The challenge is in tuning those. Why did I choose $50? What if I chose $49? Would it work better? Like, what would it actually look like? And so there's a whole branch of this mathematics that focuses on that. And the big one is this distributed random forest. So this is basically an idea of how do you combine multiple decision trees and put them together. So it basically kind of you can think of it as like averaging them together, and it kind of comes up with some sort of thing completely between all of them when comes up with some confidence. And it constantly tries all sorts of different patterns of distributed decision trees to kind of even get some good feelings about which ones are working and not. So I just want to highlight that some of these are not necessarily like 100% mathematical. Now the next one is the complex one. This is the fun one. So in this one, I'm going to reference just the image from this ACM Magazine for Students XRDS, written by this Abdurrahim Hosni, who this is actually a really good article. I have the link in the deck that talks about what the neural nets are actually doing and how it applies. But what I really want to show is this image. So this is a neuron. Okay, I think they actually he pulls this from the Stanford course, Sarah course. But the neuron, the dendrites, everybody knows what a dendrite is, right? So the dendrites are where you're basically going to get your sensors have inputs. So you can think, your ear, right? Here's something, and it turns into an electrical signal that then gets applied to the dendrite. And then I have a neuron that is dedicated to hearing that processes that in the nucleus. It takes that signal, does something to it, and then puts it on the wire. It puts it on into an axon. The axon is then connected to additional neurons. And so there's a whole chain of signal manipulation that actually happens in our brains. And what the deep learning modeling is actually doing is mathematically trying to model some of that and figure some of that stuff out. The really fascinating thing about this is that there was a research paper published where they took, I can't remember what animal it was, but they took the neuron that was used for hearing in an animal, and they disconnected it from the ear, and they connected it to the eye. And the neuron transformed into a seeing neuron, which is really magic, right? Like that's the whole point of these things, is that they're actually learning. They're learning what the sensor is. They're figuring out how to process the signal in a way in which you'll be able to use that information later. And that's what the neural nets do. Now, the problem with this is that they are completely black boxes. Whereas the other things were easy for us to maybe visualize, show some charts and graphs and things like that, these wind up becoming, so this is an example of the neuron as it's drawn in the math, but it's basically, you've got the same thing. It's the inputs, I do my processing and I get something out. And then what happens is we look at them through chains of these. These are called layers. And you'll hear this term, but basically some of these neural nets may have way more than 3 layers. They may have like lots of hidden layers and you don't know exactly what's happening. They're all communicating with neurons in the way and they're all transmitting the signal and manipulating the data. But honestly, this is actually probably one of the most interesting areas to watch from like a PhD perspective, because there is a lot of people trying to figure out how can we make sense of the data and the metrics and stuff that's coming out of these types of algorithms to help us understand them better. But honestly, that's way above my pay grade. All right, so that's the neural net. And fortunately, I think our neural net has actually completed. So let's take a look, and you can see here that it is predicting a whole set of data. And actually, I'm going to pull this up in H2o Flow now so that you can see what this did. Right here, F5. Okay, so remember, I ran the PowerShell code. Again, this is that MNIST data. I was running a deep learning, the neuron type training against it. So now, if I run get models, I actually see the neural model that I had. I can also look at the predictions that were running. So this was the one that was run against my test data. So actually, I want to look at that more closely. And here, I can see, first of all, I can see that the MSE was 0.5, which is OK. And I can inspect this data. Oh, sorry. Oh, there we go. OK, so I don't know why I'm having problems with this. That is not it. Hold on, let me just, actually, let me do it in PowerShell. For some reason, I can't find it in Flow right now, but I know it's there somewhere. And I happen to have all of this data here, so I'll just use it here. So the last thing I was doing was looking at return.frames.com. So this is the output from the last command I ran, which is looking at the predicted data. And you can see here in frames.columns, there's a data. And this, so what this is, and I'll just look at the top 10. Oh, sorry. Jeez, that was weird. Don't normally do that. Anyway, so here's the results. So, and I'm gonna, I'll just open it in Excel. This way it'll take less time at this point, because normally I would do this in Flow. But all right, so this is the test data that came back. It was basically, what it was doing is it was looking at the pixel arrays. Oh, I had it loaded in memory. It's all right. So here's the pixel arrays again. So this is the prediction, the stuff that I was just running. And what you can see is, so for the first number, it was in the number 7. And our model predicted 7.29. We averaged that down to 7. The next one, 1.6, averages to 2. So therefore, it predicted that that number 2 hand-drawn was actually a 2. The 1.0 applies to this 1.0 here. This one worked out pretty nicely with the test data. So 0, 4.2 comes down. So that's what I did. I just bulk tested this entire test set and seen what the predictions look like. I'm just comparing them manually now, even though the MSE actually showed me the mathematical bits to that. And now at this point, I can actually through PowerShell submit a pixel and say what number is this, right? Now you can start thinking about the practical applications of this. Think about your logging data. Think about anything that the creativity is really, it's in your hands at this point. If you know your data sets and you think that there's an interesting application to it, there's probably is an interesting application to it. Okay, so that was the neural net. I've got one more thing I want to show you guys on the math side. And now I'm going to actually demo this one and how we do this in a second. So this one is GNU. And I can now move things again. GNU free documentation license credited to Chire. Okay, and this is what this is illustrating right here is it's illustrating a mathematical model that is basically finding the clusters. So this is the Netflix idea. How do I take all of these data points that exist and find the commonality? And the way these algorithms work is you usually tell it how many things you're looking for. So in this case, we're going to actually be doing a demo where we will look at we will basically bucket them into 3 different categories. And this is just a mathematical representation of what that kind looks like. Yeah, and obviously, as usual, it gets more complicated with more inputs. You wouldn't be able to visualize it as cleanly, but I think the idea is sound for you to at least understand what we're actually doing. It's basically finding the points at which it wants to break this into 3, and it's then calling each of those a group. The illustration itself is actually in the algorithm implementation in that how it's changing the lines over time and manipulating it, but we don't have to go into that. It's just more about visualizing what's actually happening. So what does this look like in H2o? I'm going to do this one in H2o. We're not going to do this in PowerShell because at this point, the stuff that we're doing in H2o, you can all do in PowerShell through those REST methods. OK, so I'm going to pull up an example flow here. Oh, also, I don't know if everybody noticed, but I was loading that data in PowerShell, and now I can see it in H2o, right? You can see all the data frames, all of that stuff. OK, so k-means example. Let's load this up. So here's a great example also of how you can take these flows, and you can use Markdown. You can apply, you can actually hand this to somebody and say, hey, run through this. This is actually how we train these data models. In this case, what they do in the examples is they give you the instructions. They tell you, OK, run assist me, and then they show you the function to run. So you can either click the button, assist me, and brings you all the way back down to the bottom, and you follow the stuff. Or the next thing it does is it shows you sort of the functions that you're going to have to call. So in this case, if I call import files, it would give me that dialog again. But they also provide you the parameters. So I can just simply import files here. So here I'm importing another data set. This is seeds.dataset. It's very similar to the iris one. So we're not going to go too crazy on that. Oh, actually, I wanted to restart this. It's all right. OK, so that data is in there. We're then going to parse the data. So we'll run the setup parse, and then we're going to parse the files. I'm just using the functions that the examples provided me. The interesting thing is when we're building this model, so there's a couple things to note here. When I hit build model and I choose the k-means, so this clustering, hold on. OK, so assist build model, here we go. What I'm selecting here, there's a couple of parameters that we're setting. C7 is basically saying ignore that column. K, because that's the column that, or actually I think it's C8. I think that's wrong. That's the column that they're categorizing. K is this number 3 is that we're saying that we're going to do it into 3 buckets. So we're looking for 3 groupings out of this data. And then there's a couple of other things here. So I'm just going to run that. We'll see if my change actually breaks anything, because I've never tried that. The model exists. I can now predict against it. And the important thing here is to look at what sort of the output looks like. So it's showing me that it's created 3 centroids, which is our clusters, and how many are in each one. And I can actually look at this data. This takes me a second. Hopefully I'll find it. Yeah, I think it's this. So there's some statistics about the data, and then here's the actual data. So it's basically doing the same thing. It's predicting. The difference here is that whereas in the past we were training with known quantities of what the names were, iris vitosa, iris versicolor, the MNIST data, or each numbers, in this particular case, we don't know what they are. They're just 0, 1, and 2. And so everything is coming back as 0, 1, or 2, which basically means that they're grouped together. So now if I run another prediction, so I can basically take that data out, I can run another prediction off of a new set of data, figure out what group it belongs to, and then I can go back and look at that group and then maybe provide it to the end user and say, hey, these are the ones that you kind of associate with. OK, make sense? All right, we're good on the k-means? Good. All right, let's move on to, we're in the home stretch, 10:03. OK, so I did the unstructured learning. The next thing I want to show you is the grid search stuff. Okay? Grid search, as I mentioned before, is the idea of taking one of these complex algorithms and not knowing all the parameters, but knowing an idea of what we want to try, and then iterating and trying all of them, and then comparing the models. So let me restart H2o so we have a clean one. All right. And let me load that again. OK, So we're going to do exactly what we did before. I'm just going to quickly import the iris data just so you can see this as a quick one. H2o, iris. We'll import, we parse the files, parse setup, sorry, then we parse. Okay, so we've imported the iris data again. I'm going to split that data into the two. So 0.9, and we'll call that train. 0.10 is called test. We create that again. And now I've got my two frames. So now I want to actually try this grid search thing. So the way I do this is I take my training data here and I say I want to build a model like we normally do. Now in this so I'll do the distributed random forest just for fun because we haven't done one of those. I'm going to basically select my training frame, select my validation, so the same stuff I normally do, and my response column class. And now this is when I typically just was hitting run and we were creating the data model. What you see over here on the right, though, is there's this grid question mark. Okay? And if you look, there's checkboxes. So anything that I can do a grid search on has the checkbox. So, for example, number of trees. And if you notice, when I click this, watch what happens next to that 50. Semicolon. All right, which means that I could probably put more stuff here. So now I can say, all right, I want to try 50, I want to try 100, I want to try 150, I want to try 200. Max depth, I want to, let's make that a grid search. We want to try 20, we want to try 40. Okay, I think that's good enough for now, just as an example of what's going to happen. But I could do this with all of these parameters here. And as I mentioned, there is this newer technique that people are using. If you've never heard of it, Bayesian optimization for parameter tuning is really, really interesting. There was a talk that an MD from 2 Sigma gave at QCon 2 years ago in New York that's online. Highly recommend it. He goes into the mathematics of how it works, but his prediction is that basically anything that accepts parameters will be embedding this technology into it over time. And the examples of practical implementation besides this that he gave was tuning your Java parameters as well as tuning your cloud templates, like the options that you submit to Azure or to AWS, actually figuring out like what the ideal optimal VM is and like configurations and things like that. It's a really interesting space. But anyway, for this one, this is not that. All this is doing is bulk iterating. I gave it a couple of options. It's going to try this one, this combination, try this combination, try this combination. So let's run that. Build. All right, so you can see it's taking a little bit longer than the other one because right now it's building a bunch of different things. It's scoring them. It's trying to figure out which one is the best one. And then we're going to see what it looks like after it's done. So it's finished. I can look, and now I see that it actually created 1, 2, 3, 4, 5, 6. Actually, I have a few more. So there's 8 data models there. Now I have to figure out which one I want to use. So I can look at a couple of statistics. There is a scoring history, so I can see what the RMSE was for each one of these. It's basically saying it thinks this one is the best one, so then I could say, all right, well, let me predict that. Let me look at that one against my test data directly and see how well it's performing. And here you can see it's actually performing fantastic. So against my test data set, the MSE is at 0.000. So this is actually a really good, we finally got a good data model for this data set. But anyway, that's the point. I just wanted to show you that that grid search works. Now, again, with PowerShell, that part, what you're going to have to do with that is figure out all the parameters you want to try, inspect the network, look at what the post data is for those grid searches, and then just apply it into it. Okay, yeah, it had 0 error. It's pretty incredible. Okay, that was that one. So the next thing we want to talk about is productionizing this data, these types of things. Yeah, Pojo, good. So in each of these data models, and I'm going to take the one that we just built, and we are going to serialize that out of the system. And the way we do that, so first of all, I'll just say get me my models. So we'll take this one that was pretty good. Okay. So I can say download Pojo. So Pojo is a plain old Java object. That's what it stands for. It's basically a Java class that you could either embed in your application, or what we're going to show you is how I can convert this using the Steam interfaces to turn it into a WAR file that you can then turn into a web service that you can then use from PowerShell without needing H2o at all. So download Pojo. That's going to grab the Java file, and I'll show you guys what's in there in a bit because using it manually is kind of cool. The other thing that happens is there's this gen model that you need to download from H2o, for which each version has its own. It's basically just its own jar file. I've already downloaded that one. This one I want to actually I want to make sure we're doing this one. So let me copy that there. Oops, C drive. So what I'm going to do is I've got a Pojo directory, and I'm going to paste this one in. And OK, so the one that we're working with is grid 6F4. All right, so that I just want to remember that. In this folder, again, I've got the H2o gen model, the thing that I just downloaded, and that Pojo file. The next thing I'm going to do is, so I mentioned that there's this open source project that's deprecated called Steam. So Steam H2o, which you can fork and build. But there's one very specific folder in here. I'm just going to, well, I was going to show it in GitHub. Yeah, OK. So there's one particular folder in here that if you build this prediction service builder, will allow you to pass the Pojo and the jar file that we just downloaded and spit out the war file. I can get this to work on Windows. I've had it working in the past. Right now, I couldn't get the class paths to work, so I just cheated, and I'm doing it on the Ubuntu shell. But basically, the service looks like this. So you have to grab it, download it, and then run Gradle commands to build it. Once it's built, there's a war file in here. You can see the root.war. And now what I'm going to do is I'm actually going to run java-jar and run one of these Jetty runners. I honestly don't know the differences. So I'm just going to run the one that looks like the most recent. And then I'm going to pass it that root war file. And so when I run this, ooh, that's new. Well, fortunately, I did process this a few times. What was that?
Maybe there's a reason it's deprecated.
Yeah, right. It's true. Now, the reason it's deprecated is actually because they've turned this one in, they're turning this one into more of a commercial product. They left the open source one, but most of the magic that they're doing now is in the paid version. OK, there we go. It was just the version of Jetty Runner I was using. OK, so it spins this up on port 8080. So now, if I come here to port 8080, I should see a nice little service. Oh, no. Oh, I see the problem. I do see the problem. Hold on. Yeah, this is the wrong war file. Something is. Let me just try one more thing. I could always. Anybody know any good jokes? Building, up to date, building, running. OK, and it's running at localhost 55,000. Let's see if that works. No, it's this. Oh, there we go. OK, good. Oh, OK, that's the right one. So we select this Pojo. Here I'm going to pass in the Pojo file that we created, which was 64F. I'm going to select that jar file that I downloaded, the H2o gen model jar, and we're going to build this. When I build this, what it's actually going to do is it's going to create a war file for me. It takes a few seconds on this one. There it goes. So it's downloading the war. Once that opens, I'll grab it. I have no idea why 8 megs is taking that long. OK, so we've got the file. Let me open it. So I'm going to take that war file. I'm going to copy it into my Pojo directory. Oops. And I'm going to basically call another Jetty runner service on this war file directly within Windows. So C drive, H2o. OK, we made it. So I've got this grid 64F .war file. So I'm going to come here to, we're going to create another shell. And in this one, I'm basically going to call from the Steam directory, which is where I downloaded the Steam and built it here on this one, the prediction service builder. So it's java-jar, the Jetty runner, which I will do that one. and then the path to the WAR file, which was C, H2o, Pojo, shoot, what was it, grid, 64F, no, WAR, okay. Also, let me make sure I kill the other service that was running that was doing the conversion, just in case we clobber any ports or something like that. Okay, so now I'm going to run this service. All right, it's running. Port 8080 by default, so now let's check out what that actually looks like. This is really cool. Hold on. Not this, I don't know what that is. All right, localhost 8080. I now have a web interface. I can say, all right, what's my sepal length? I think it was a really big one. It's 30. My sepal width was 15, and the petals will go 0.1 and 0.03 or something like weird. Anyway, now this service, I can say predict. So this is not running in H2o anymore. This is running, just a web service that I pulled out, and it's a WAR file. And here you can see it comes back with my data. It says Setosa 0.879 probability. There's a very small chance, less than 1%, that it's Iris virginica, though. The other nice thing is now I can actually craft these URLs. So this is a complete REST service. So I can take this, and we can invoke REST method in PowerShell. And say invoke REST method. And so what you can think of is, the reason I show this demo is I like to think of the pipelines you need to productionize these things. Like you can take that Jetty runner conversion thing, put it as your part of your build process, build it into the service, and then run tests against that. But anyway, here's the invoke REST method on this. Oh, we're going to need quotes because there are some ampersands and all sorts of nonsense in there. Okay, so here you can see it comes back with the exact same data. So now I've accessed it within PowerShell. I can access it from anywhere. It would be kind of interesting if we can figure out like Pojo to PowerShell or Pojo to .NET. I think there's some projects that people were working on, but it's way too complicated. What I will show you is what the Pojo looks like, because the other way that you can do this is you could just compile quickly a Java application that uses this Java class and uses the function in there, which I will now show you. This took me a long time to figure out, so I'm very proud of this. Because this is what the Pojos look like. Let me just make this bigger. There are enormous amounts of code with lots of nonsense. And crazy amounts of functions and all sorts of weird words, and who knows what's going on. It's dividing all sorts of things. This is the magic. This is the mathematical model. Like this is actually, I mean, this is an algorithmic model, I suppose. But anyway, the point is that there is a score 0 function. And actually, it looks like I went to, let me go up to the top. Score 0 function. This is all you have to call. So if you were to load this class, build a Java application, and you leverage this, it takes a reference to a data structure, so it's to a list of the inputs. And then what it does is it provides you provided a reference to an array for the outputs. And so when you run the prediction, it's going to load that into that collection there. And it shows it to you. This is the place where it was really weird. It shows you in that 0.9999. And the other thing that's kind of strange about it is it doesn't tell you what type it picked. It actually forces you to know that the first one, like the order at which they're listed, which I can't even remember where you see them, is the order that they come back in. So the score function doesn't actually give you that information. It just gives you those 3 numbers, and you have to interpret them. Cool stuff. All right. Let's see what we have left. I think I flew through this. This took me a lot longer. Oh, AutoML. Last one. Yeah, we really burned through this. I swear this took me an hour and 45 last night. All right. So AutoML, we are going to look at one more of these. So for this one, I do want to create a clean one again, because this is basically going to generate a ton of models. Oops, just run it. And as I mentioned, this is the interface. Like if you don't know what algorithm to use, you're not sure what to even try the AutoML, see what it comes back with. It'll take some time. This, even against the Iris data, this will take you like a good hour or so. There are some parameters to help it exit early, and you could always kill it and look at the models generated. Like you don't have to have it run, which is what we're going to do right now. But there's a separate function called run AutoML. Oh, let me load the data. Apologies. Import files. Do this all again. H2o Iris Okay, import parse setup parse. Okay, now we can do an AutoML. I'm just going to do it on, I'm not going to split them this time. I'm just going to, to make this a little bit faster. So run AutoML. AutoML takes a training frame. It's the same things as the other ones did. Which one is the response column? Do you have validation for data frame? In this case, I don't because I didn't split them, which actually may kind of show weirdness when I'm looking at it. But that's all right. We'll just run this now. There's some additional things that you can say. Okay, so for early stopping, I want this to only run this amount of time. Like you can set some parameters here to make sure that it doesn't get out unwieldy and out of control. And then I just hit build model. Now it is trying a series of algorithms. It is trying them in parallel, and if I happen to have Spark behind the scenes and was doing sparkling water at this point, it would be distributing this across all of my clusters. Everything out there would be training up models and testing them and validating and deciding which one is actually the best one. Again, because I didn't do the validation, it's not really going to be fair. But I will say also that this is happening in parallel. So right now, I can see the models as they're getting generated. These are all of the models it's trying, which is kind of cool. And then I can look at any of these individually, and I can compare them. I can see how they look, all out of the box. I mean, there's more you can do with this stuff. If you get really into this, like you can spend a lot of time figuring out how to, what's kind of interesting is as you lose the mathematics for visualizing how the data model actually works, you can actually apply mathematics to the various models that exist and how they're out there to kind of visualize like which ones are working the best and not and things like that, which is kind of fun. But there's a whole, this is where data scientists spend their time, tuning these things, making sure they have it right, figuring out the next things that kind of come into this world are weirder things, like what happens when I introduce new data sets that completely blow away my old model and don't make any sense anymore and they're not valid. Also, how do I productionize these things regularly? Like, if I'm putting them through a CI/CD system, like how do I test this? And if I make a change to one of these models, like that has some serious impact depending on like what that code is actually doing. For most of the PowerShell stuff, probably, hopefully not. But if any of you guys get really super creative with this and do some interesting practical things, you may want to think about those things. Okay, so that's going to keep running, and actually I'll just kill it for now so that we can take a look. Here it is. So we'll cancel that. It's up to the GBM. It's going to actually try pretty much all of the models that were out there. Anyway, I can now look at this, and it tells me here's the best ones. These ones were like super fit. Unfortunately, because I didn't have the validation set, like we can't tell which ones these actually are working, because these are all just super fit to the actual training data at the moment. You can also look at there's a lot of log information. And then each of the models themselves, you can see the parameters that were set. So if I say it like right here, I can say model parameters, and I can see what was used when this was created. So now I can go and find the ones that I liked, and in the future, I'm not going to run this whole AutoML thing. I'm just going to run these ones in a grid search and see which one comes back the best. It was a lot of information. We sucked up a lot of time. The last thing I want to do is just leave you guys with the resources. There's a few out there that I think are worth the time just looking at. First and foremost is the H2o.ai portal. That's their documentation. There's the H2o algorithm documentation, which I showed you the link to there. That's basically all the parameters and what you can set there. My blog post with the code samples, and I'll be posting this to that blog. It looks like we're all posting our own stuff it looks like there's no central place, so I will post it to my blog. And but right now you can grab a lot of you can get the Iris Virtuosa deep learning scripts right from here. And I think there is a MIT license on these. I can't remember where I stored them. I think they're in Git. So feel free to use and in any way you see fit there. And it kind of walks through a lot of the stuff that I was talking about today as far as how the REST API works, how we build the models, how you use them, et cetera, et cetera. It doesn't go kind of deeply into a lot of the stuff I talked about, but just the reference example to get yourself started. I also highly, highly, highly recommend the Stanford Coursera course if you really want to have, if you want to understand it a little bit better. That Coursera course will have you implementing the algorithms from scratch in some cases. It's a lot of matrix math. What I will say is if you do go into that course, the teacher, Andrew Ng, who is the guy who invented the cat categorization algorithms against YouTube to find cats. He was like looking for cat videos. Anyway, he tells you very clearly, do all the homework, but when you get to the neural net one, don't feel obligated to do the homework. I spent 2.5 months working out the mathematics and trying to get the implementation right to get it all to work. I did get it to work. I'm looking back at it during this course, like as I was preparing for this, I have no idea what I did. So I will recommend what he says to skip that part of it. There's great stuff in that neural net one. Like he has a bunch of good videos and things that describe it and talk about how the math actually works. But yeah, I would highly recommend not actually doing that portion of it unless you're masochist like I am. So Sado. Anyway, H2o Coursera course. Oops. This is a new one I found. So apparently H2o put out a Coursera course. I haven't tried it yet, but since it exists, we might as well use it. And then there's an O'Reilly book, The Practical Machine Learning with H2o. All the code samples there are usually in Python and R. Another thing that's kind of strange when you look at code samples in Python and R, and something to keep in mind, is that they don't map to the H2o flow model. Because there are SDKs and libraries, they've gone and basically abstracted all of that stuff. So you only see one import file function instead of the 3 that we've been doing over and over today. Okay. And with that, Twitter handle Tome, I can actually have time for questions. I don't know if I have answers for any of the questions, but all right. I guess I'll give back to 15. Thanks, guys. All right.